Start streaming. Okay. So stream settings. Yes. Okay. Yeah, it looks good. Okay. Hopefully that quality is good. Okay, hopefully this doesn't fuck me over. Okay, so the first thing I'm gonna do is I'm actually gonna get rid of these because yeah, we're using unsigned int in a bunch of places. Okay, so we're gonna do the handshake now. We've got SHA1 working, we've got base 64 encoding working. Now we should be able to complete that socket handshake with our C++ server. So, let me just check real quick that OBS is good. OBS looks good. Okay, so uint, we're gonna change to uint32t. And then long, what else do I have? Uint 64, or was it U64? It was U64. So U64 we're gonna replace with uint64t. And that should be good. And anything else I can kind of clean up? Yeah, I'm not crazy about this music. Okay, so we have SHA. The only thing I was thinking of is that we have SHA here, and then we have base 64 encoding, and technically we don't have to convert it to hex and convert it back. But I've already got this. Like we could just return a char array and just pass the char array in here, not have to do this conversion to hex, conversion from hex. That probably makes the most sense to do it that way. No, I didn't save it. Okay, so we're still good. The code is still good. Okay. Yeah, I might change that. I might clean this up a bit because it doesn't need to convert from a hex and then we're converting back from hex. So instead what we would have is when we do SHA, what I could have it do is let's worry about this later. Maybe I'll clean this up later. Let's do the actual handshake. So back to the handshake. So we take the sec WebSocket key in the handshake, and then we concatenate that key with a magic string, right? And this magic string is this guy here. I've also got it in here in the Wikipedia. Yes, yeah, it's this magic string here, right? So we concatenate whatever that is with this magic string. Do the SHA of that. Now, for now, let's just confirm again that this is working. So let's run Fenrir, and then I'm gonna try to connect here. So this is what we've generated from, well, okay, the hash is going to be different than theirs, so this is actually a test that doesn't make any sense. Let's just do this and see what happens. So we do that, we get our hash, right? So we do that, we get the hash value. Then we're going to encode this to base 64, right? So this is going to be base 64 code the hash, and that's it. All that work just to do these two simple steps, and this is what we should be returning back to the client. So let's see what happens with that. Okay, what's happening here? Connection established. We receive 478 bytes. Client has closed the connection. Oh, I think we also need to set other things in the header. I thought it said, yeah, we have to send this stuff too. So we should be sending this back. Man, I really want to see what I'm sending back. Because, so we need to set upgrade to WebSocket and connection to upgrade in addition to our socket accept. So upgrade should be WebSocket and connection should be upgrade. So let's do that here. So upgrade should be WebSocket, and then connection should be upgrade. Let's make sure that's correct. Yes, okay. Now let's, should be response So let's see. Okay, let's see what happens. It failed. Can I see what I'm getting back here? So we got HTML, then we do test. We're still not getting any information back. Wait a minute. Okay, get person info. It shouldn't be called guess. I'm not getting this. This was a test for something else. Let's call it Handshake. Wait, no, I'm not looking for that. I'm looking for... All right. Okay, so this is what we have. Call the endpoint, and then we write the response. This is what I'm looking for here. So writing the response, we should have this. Okay, that's why we weren't actually passing back the headers. So HTTP1, whatever the status code is, status meshes, new line. Then we need to add all the headers and then finish the whole thing with a new line. And then send that data back. So now what we're gonna do is we're gonna do for I believe this is right. Data is it a reference, or I don't remember if it's a reference or a pointer. Data is equal to, so we have to write the name of the header, colon, space, and then whatever the value is, and then a new line. So that's kv.first, name of the header, plus colon, space, plus kv.second, plus new line. There's no error, so I think we might be good here. So before we send out the response, let's see what we're passing. So what's our data? HTTP 1.1, 101, switching protocols, new line upgrade, WebSocket, connection upgrade, this thing, new line, and yes, that should be it. Okay, so now we're sending back all the information that we have. How come I don't have any hinting anymore? Visual Studio, oh, it's because I'm running. Alright, this is a pair. I want to see exactly what I'm sending back to make sure that the packet I'm sending back is correct. Okay. So what's happening? We're doing this. Switching protocols. That's what we name it. Yep, switching protocols. Upgrade connection. What is going on here? Is it that my WebSocket accept is wrong? I don't think that's wrong. Is it something with the actual HTTP response that's wrong? That's what I'm wondering here. WebSocket accept. Okay, well, let's see if we can do something from the WebSocket side. Connection to this failed. We're doing this plus this key. Hashing it. Hash. And then we encode that hash. Okay, well, let's first do a test to make sure all of that's correct. So okay, so this is our key, right? This is the key. Now, if we take this key, I want to make sure that this no, so it's this along with a magic number gives you this, and then you base 64 encode it. I don't think this one does proper encoding. It adds a bunch of bullshit to it. Hmm. Oh, okay, maybe it is correct. Then we get this. Right. Now, what do we have here in the response? Look at Visual Studio. This is just top quality software, isn't it? Look at that. Look at this. I now can't do anything. Look at that. This is what happens when you start programming stuff in Ionic. Yep. Okay, that's a completely different key. So that's completely different. So okay. Let's go back here and look at their example. So their example was if you have a key like this and you take this key and then you concatenate it with this magic number, you get this, right? And then once you base 64 encode it, yeah, this base 64 encoding is completely wrong. And I'm not sure why. Yeah, I'm not sure why, but it's wrong. Base 64 online. Not only that, you want a base 64 encode. You want to encode the hex value. That's the thing. So this is the hex string. Base 64 encode. We get this, which is that. Okay. That's correct. So now if I go back here and I look at my request and I look at the key, we go back here, we put the key in. This is the hash. If I come in here, I put it in here, we get this, which looks correct, right? This is the key I have. Hold on. This is the key I have. Right, that looks correct. Yeah. Okay, so what I'm sending back looks to be correct. So what isn't working? Why isn't it accepting the response? Here's my response. Why isn't that working? I think this part's correct. Why isn't this working? Well, let's take a look at WebSocket. The header looks right. And put an extra this after the last one to indicate the end of the header, which is what we have. So WebSocket, and you do this. Okay, so let's add this stuff then. Add event listener open, and it takes an event. Open, and it takes an event. I think there might be an error one as well. Writing a client application. So you create your WebSocket. Where's the good respond? This should use the URL scheme WSS, although some software may allow you to use the insecure WS for local connections. On air handler. So add event listener. Here. So socket.add event listener. Okay, so let's open that file. Let's go to Fenrir. Let's go to this guy. Actually, I'll open it in the same one. Yeah. Okay. So, okay. So we have our socket, right? And then I'm going to say socket add event listener. Is that what it is? Error. Add event listener, lowercase a. Gonna run Fenrir. Okay. So there you go. Invalid frame header. Invalid frame header. Event is trusted true. Right. WebSocket connection failed. Invalid frame header. Now, the thing about that is that, oh shit, is it assuming that I have to write to... Oh, you can also just say on error. So instead of saying this, we can say socket dot on error equals this. Right? So invalid frame header. Like, I'm wondering, is that this thing? Invalid frame header. I'm just good. Is it that the connection is good? Well, let's look at the other things that we can do here. So we have on error. We also have open. When a connection is open. and then there's message, and then there's close. So let's add those then. Socket.open on open, I'm assuming is what it is. Okay. On open, on message. Why is it now not giving me that same information? Oh, wait a minute. Open. So wait a minute. It does open? Okay. Okay, let's try this again. Let's kill Fenrir. Rerun it. Ah, okay. So the connection is open. Client connection established. Bytes received. We sent our response out. How come I can't see that in the network tab? Ah, boom. Okay. So, giga-D. Here we go. Look at that. So, the response, connection, upgrade WebSocket, and then we accept this guy. Boom. Status code is 101 switching protocol. So handshake is good to go. The handshake is good to go. And now the problem is, then we get an error, invalid frame header. I think it's sending data to the server again, and then the server is just not responding properly, right? So client connection established, bytes received, then we respond, right? Let's add that information in there to make it a bit more clear what we're doing. So write response. So in write response, we do all this. If we fail, then we say failed to send client data. Otherwise, if it's successful, and then we close the socket. Otherwise, we'll say failed to send client data. Otherwise, we'll say failed to send client data. Maybe instead failed to write response. Failed to write response. Failed to write response. Response sent. Response sent. And then we want to have how many bytes? right? Data dot size is how many bytes. And then what's the message that we say? On socket data received. So client connection established. Here I'm going to put a new line just so that we break it up. Client connection established. Bytes received is 478. Oh no, wait, I'm breaking it up in the wrong place. It should be, so bytes received. So client connection established. Bytes received 478. Response sent, so we wrote 129 bytes. And then failed to receive client socket data 10053. So the client then sends some other information, and I'm not sure what that information is. But now we're at the next stage. So I think we've got the handshake working. I think we have the handshake working. So let's do that next. Let's assume that the handshake is working because it looks like it is. Here we didn't get the response for whatever reason, but exchanging of data frames. Either the client or the server can choose to send a message at any time. That's the magic of WebSockets. However, extracting information from these so-called frames is not so magic. It's not so magical experience. Although all frames follow the same specific format, data going from the client to the server is masked. Here we go again, man. Using XOR encryption with a 32-bit key. Section 5 of the specification describes this in detail. Okay. Okay. Each data frame from the client to the server or vice versa follows the same format. This is the format. The Wikipedia article is a bit more clear about this. So this is what's sent back. So these are bits. So these are in bits. But this is just one bit. Fin indicates the final fragment in the message. 1 bit. This is going to be a lot. This is going to be quite a bit. What are we looking at in terms of time here? Okay. RSV must be 0 unless defined by an extension. The operation code. Opcode. The mask set to 1 if the payload data is masked. Masking key. Payload data. Payload data of the fragment. Okay. The payload data sent from the client should be masked by the masking key. The masking key is a 4 bytes random value chosen by the client and should be unpredictable. The unpredictability of the masking key is essential to prevent malicious applications from selecting the bytes that already appear. The following algorithm is applied to mask the payload data. I mod 4 transformed octet I is the original octet, so we're looking at 1 byte, 8 bits. You take the original. Oh, this might be the exclusive OR encryption they're talking about. So you take 8 bits, you exclusive OR it with this masking key octet, and that gives you this new octet. The masking key octet at J is I mod 4. The one problem is I don't even know what I don't know what the client is sending to the server. So we initiate the handshake. It might be sending a message saying that it's connected or something. Okay, let's go back to this. So these are the actual bits and these are the bytes. So it's in total we have 4 bytes of data. Is that right? Well, that's one byte. There's only 2 bytes here, right? It's 2 bytes. Yes. 4 bytes. Okay, no, yeah, we have 4 bytes total. Right? Okay, I've got to now guess what's happening here. So we have 4 bytes total. So we have 1 bit, which is the F. Then we have RRR. We have an opcode, a payload length, extended payload length, a bunch of this stuff. I don't know what the hell that is. This means that a frame contains the following bytes. The first byte, bit 0 is, oh right, so the first byte, bit 0 is fin, then there's this, an opcode. Bytes 2 to 10 are the payload length. So we have this stuff. We have the payload length, opcode, a mask, and then the payload length. Bytes 2 to 10 of the payload length. If masking is used, the next 4 bytes contain the masking key. The mask bit tells whether the message is encoded. I'm not going to encode the message because I'm not dealing with sensitive data. This is just for like a game. The mask bit tells whether the message is encoded. Messages from the client must be masked, so your server must expect this to be one. Okay, so I'm assuming WebSocket's gonna do that. When sending a frame back to the client, do not mask it and do not set the mask bit. We'll explain masking later. Note, you must mask messages even when using a secure socket. RSV 1 to 3 can be ignored there for extensions. The opcode field defines how to interpret the payload data. 0 for continuation, 1 for text, which is always encoded in UTF-8, 2 for binary, and other so-called control codes. Oh, you can send binary. That will be discussed later. In this version of WebSockets, 3 to 7 and have no meaning. The fin bit tells whether this is the last message in the series. If it's 0, then the server keeps listening for more parts of the message. Otherwise, the server should consider the message delivered. More on this later. This is going to be a lot. This is going to be involved. I thought this was going to be fairly simple. No, this is going to be quite a bit. Decoding payload length. So where do we start here? They didn't get to the XOR stuff again. Message fragmentation, ping pongs. Oh, they actually have one like writing it in Java. Oh, and look, we're doing what I'm doing here. Right? They're encoding it. It says they're gonna get to that later, but XOR encryption, it's not very complicated. You just exclusive or something. That's all you do. That's all XOR encryption is. So data going from the client to the server is masked using XOR encryption. To read the payload data, you must know when to stop reading. That's why the payload length is important to know. Okay, so they're gonna come in with some data. It's not going to be an HTTP request anymore. So that's the thing. It's not going to be an HTTP request anymore. So that's gonna be a. So we're gonna come in. We're gonna receive some bytes, and I think that's what we're getting from. I don't know why it's not always doing this. We're not getting the accept anymore, which is a bit strange. Okay, so why failed? So we then receive 10,053 bytes from the client. And it fails because our buffer size, right? Our buffer size is only 1,024, right? Our buffer size is how much we can read at a time. So we read buffer size up to a buffer size amount into the buffer. The result is greater than 0, right? So we receive this many bytes, and then we call on socket data received. So we receive data. Oh, I'm sending this back. This was a test. I'm just responding with whatever was sent back. Yeah, this is no longer the case. Yeah, this is no longer the case. So on socket data received should go down to here. We then should send that out, write the response. Right, okay. Let's rerun Fenrir. I forgot about that. We were sending just garbage back to it, so it thinks there's actually a response there. So we received 478 bytes. We sent out 128 bytes. Then the client closed the connection because of an error. But it won't say why. And why does the error start changing? On error. I don't know why that started to change. Okay, there you go. Now we get... Hey, there we go. Okay, it's doing something where it's trying to maintain the connection or something. So there we go. So client connection established. And client connection established. We received 478 bytes. We sent 129 bytes back. Then nothing should happen, and that's right. So we just get type open. So we have an open event. We've now opened a connection. We're connected. Okay, now here we go. Now let's actually start by sending a message out to the server and having the server handle that message. So how do we do that? Let's go back. So sending data, it's just text, right? So you just say send, and then you just send the text. You can send data as a string, blob, or array buffer. I think a blob is base 64 encoded binary. Blob, which is a file-like object of immutable raw data that can be read as a string or binary data. So you can send it as, we can send binary or we can send a string. It's an array of bytes, a byte array. You cannot directly manipulate the concept of an array buffer. So you can create one of the typed array objects. So let's start with a string. Let's just send some data. So on open, when we connect, we will say console.log socket connected to server. We'll say connected to server, and then we'll say socket.send hello there. Right. Now I'm gonna disconnect the server, refresh this, and now on socket data received, that's the thing, we're gonna get more socket data, number of bytes. This is the socket. Here we're handling it like an HTTP, right? We're reading a line, we're doing that. It shouldn't be this way once we're already connected. This is just to handle on socket data received. This is the HTTP request response stuff. That shouldn't be done again, right? So if we run this and then we do that, connect it to server, so we've got the handshake, and now bytes received, it sent 19 bytes of data, invalid request line. So it's not trying to interpret it as an HTTP request, and it's not an HTTP request, so it's not going to work. So what we need to do now is we need to on socket data received, So on socket data received, what's the index for? Okay. This is all for HTTP, right? On socket data received. On socket data received, we want to check, is this HTTP data or not? So do we already have a handshake for this socket? To accept the connection, and then we just start this loop where we're just reading data in. So on socket data received. I think we need to have our own socket that can, so we'll keep track of, so we'll have a socket, and then we will also have so bool handshake if we've already initiated the handshake, right? So what we should do here, except we have a client socket. If it's invalid socket, then it doesn't work. Otherwise, client connection established. We have a new socket. Socket is equal to client socket. Handshake is false. We haven't done the handshake yet. I think maybe this should go up here. Socket handshake is set to false, and then maybe we don't even have this. Socket, listen socket. Yeah, don't name it socket. That's one thing. Client socket. So client socket handshake is false, and then we accept the socket. So we have our client socket, and then client socket dot socket. If the socket's invalid, then okay. Client connection established. On socket data received, it's client socket. All right, we just pass that in. Socket. This is actually a socket. Yeah, but yeah, they use the name socket, which kind of is not a good name, but so it just takes a socket. On socket data received, Now what we should check is if socket dot handshake right on socket data on socket message. So if we already have a handshake, then it's a message and then we return. If it's not, then we handle it like this. And then we write a response, and for the response we need a socket. So socket socket. Okay. Yeah, so it's just socket. Right response is just socket. On socket data received. If the socket dot handshake, then on socket message and return. Otherwise, we do this. So we can put that at the bottom here. So this is handshake. This is just stuff I was working on for testing. I'll get rid of that. So this is the handshake. So add an endpoint. This is more generic. This was more generic for like a HTTP server. I think I might pull this out. Because we don't need to handle generic HTTP server stuff here. Like, we know it's going to be a get endpoint. Split path into elements, test. Endpoint is handshake. We don't have to do this. Yeah, we don't have to do this. So we're gonna say on socket message. So yeah, we could. Yeah, you know what? I don't think I would do it this way. Yeah, I wouldn't do it this way. Handshake is false. So when you get data, bytes received, you then check here, if handshake. So if we already have the handshake, then we're good. Right? Right? So if we don't have the handshake, then we say on socket data received, do that stuff, go to the handshake. If we already have a handshake, then else if on socket data else, then we say on socket data received. This should be a different function, and basically the function is like we try to initiate the handshake. We send the response back, and if we successfully send the response back, then we have the handshake. So if on socket data received is good, then we're good. Then we say handshake is true. If it happens to be false, then something went wrong, and so we would probably close the connection. Yeah. Close connection. Why is the to do like that? That's kind of weird. I don't want that. Otherwise, if we already have a handshake, then we say on socket message. So this should be, instead of on socket data received, it should be on socket handshake. Right? On socket data received should be on socket handshake. Right? Here we'd say on socket message, and then we pass in result, which is the number of bytes, and then we can pass in the client socket. Now we actually don't need to have a socket, right? In fact, we can rename socket to socket. Socket. Yeah, we can get rid of this. We can get rid of this. Client socket. Delete that. And client socket, client socket. Yeah, so we don't have to do this anymore. Yeah, this guy here, get that. Oh, and then this guy here. Socket handshake, number of bytes. I'm trying to go to my new naming convention. On socket message. So on socket message, so we've received this many bytes. This is the socket. What do we do knowing that we have a buffer? Can the messages come, is all the data going to be in one message, or is it going to be broken up? That's what I want to know. Okay, we have some errors. Client socket, right, this is socket. Okay. On socket handshake. What's the problem with this? Oh, so on socket handshake should be a bool, and if everything works, then it should return true. So it's possible that there's an error. I think we should write the response and have write response do this as well. And if there's an error when we send the data, then we return false. It did not work. Otherwise, we say bytes sent return true, and we don't need this. On socket handshake, and then on write response. Set a breakpoint there. We got an error. On socket handshake. Right. When we do the handshake, if there's an error, any kind of error, we say false. This is, I'm gonna move this out because I don't think I'm gonna write an HTTP server. I thought I needed to. I need to write a WebSocket server. I don't need to write an HTTP server. So I may not continue with that. I might remove that code. That code's there to handle a general HTTP server. Yeah. So we're running. I don't know why it does that. So it's like it still holds on to the connection. It's just things aren't being cleaned up or something like that, I think is the problem. Yeah, like see, it never connects. It just goes right to an error. Bytes received, bytes sent, and the client has closed the connection. It's this weird scenario we get into. I think what we should do is we should just close the connection. Simple as that. Okay, handshake is true, otherwise close the connection. Right? So, so if we already have the handshake, then on socket message. Otherwise, we say on socket handshake. If it works out, we're good. If not, then close the socket. I think the problem is this guy hasn't closed his socket or something, and now, yeah, see, it's still trying to connect, and it can't, which is correct. But now when we try to connect, yeah, like it I can't get it to a point where it connects, and then it's good, right? So client connection established, bytes received 478, bytes sent, so we replied with 17 bytes, and then the client closes the connection. And it doesn't say why. Oh, the naming, I think the naming matters. I think the naming matters. I think the naming matters. Probably not. Yeah, probably not. Yeah, it's like the socket's connected, but it doesn't know what to do. This is bad because I can never send information. It never disconnects the socket to the server. It's like it's still trying to connect. Do I have to close the connection? Using JSON. So it should be event.data. Okay, let's close the connection. So if there's an error, log the error, and then we're just going to try to close the connection. Even if it's already closed, we'll just attempt to close the connection. So we receive the 478 bytes, and then we send the 17 bytes out. We do the encryption. We do the handshake, and then it immediately closes the connection. This shouldn't happen. We should have, and it never shows here that we've connected, right? So on open, connected to server. This never happens. Why does this never happen? I don't get it. The error isn't happening here, that's why. The error is happening there, right? So we're here, running, and then the error happens here, and then it triggers this as well, error. But this is the connection to this failed, and it doesn't say why. Like, I don't get it. How come it was working before, but now it isn't? Is it because I don't close the connections when I like terminate the program? Is that why? I don't get it. We receive the handshake, we send the handshake out, and then the client just doesn't know what to do with that. And it doesn't even show that it responded, that it received that response. So I'm curious, if I change if I change the port number, for example, if I change the port to 8471, and now I run this, and now I go over here and I change the port to 8471. Yeah, how come it works sometimes, but then other times it doesn't? Okay, is it that I fucked something up when I did all these changes? $17 bytes doesn't make sense. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 17 bytes doesn't make any sense. It should be more than 17. Right response. It takes a socket. I think I fucked something up in the socket. The socket. I mean, okay, oh, there you go. That's why. Oh, that's fucking why. Yeah. I renamed this by accident when I changed the name of everything, so that's why everything's all fucked up. So there's the problem. Okay, I'll go back to port 8472. That was my testing port. We'll run. Okay. Yes. And then here we'll go go back to 2. So yeah, there we go. And now we receive 19 bytes, and here we say connected to server. Okay, back in business. I fucked that up when I was renaming stuff. Okay, so we're back to where we were at. Everything's working well. Now we're here. So on socket message. So we received a socket message, and here we are. This is how many bytes we received. That's in the buffer. This is the socket. What do we do? Let's go through this again. So we have so this will be in the buffer, right? So we can read this from the buffer. So the first byte is The first bit is the fin. RSV123 we can ignore. I think we ignore the opcode. Bytes 2 to 10 are the payload length, right? So this is the first byte. This is byte 2 to the end is the payload length. Bytes 2 to 10. So you have RRR, those R's, which we ignore. I think this kind of stuff we ignore. Then we have the opcode. The opcode is 4 bits. Then we have the mask, which is 1 bit. The mask flag, and then the payload length. It should always be masked, so I guess I'm just gonna assume that it's masked. But I guess we'll check for it anyway. Then we have the payload length, and then we have extended payload length. Right, and then extended payload length, and then a masking key. I don't understand how they have this set up like this. Bytes 2 to 10. Oh, I guess they mean like the 0th byte. Bytes 2 to 10, payload length. If masking is used, the next 4 bytes contain the masking key. So we can read this, okay, and then we can ignore that. I think we can ignore the opcode, and then we get the mask flag. So we're literally just reading these from the server, from the buffer. So the buffer is just an array of characters. So we're gonna look at our first byte. Let's get the fin and let's get the mask, I think. Then you have payload length. We can ignore this. Then we need the masking key. And this whole thing is 4 bytes in size, right? So 4 bytes is an int, 32, right? 32-bit integer. If masking is used, the next 4 bytes contains the masking key, right? And the mask is that flag here if we are using masking, I believe. If mask is set to 1, right? Masking key continued. They just have it written kind of weird. Then you have the payload data. All subsequent bytes are payload. The mask bit tells the message. It tells whether the message is encoded. Messages from the client must be masked, so your server must expect this to be 1. I'm just gonna assume this to be 1. Your server must disconnect from a client if that client sends an unmasked message. Okay. So I'll check for that. When sending a frame back to the client, do not mask it. The opcode field defines how you interpret the payload data. Oh, so what type of data is it? Okay, so let's extract fin, opcode, mask, and payload length. So basically we can read an int from the buffer. We don't have to do that, I suppose. I'm going to put this off to the side as a reference. So let's do this now. So we have our buffer. So I'll just have this as a char, I guess. Fin. Is that? So fin is, so you say buffer, the first byte in the buffer, and we want the first bit. So Do we have to worry about endianness here? Fuck. Yeah, I'm wondering about that. Do we need to worry about endianness? Yeah, I'm not sure if the socket deals with that or not. Up until now, we haven't had to worry about. I don't think we do have to worry about it. Yeah, I'm not sure. So So for example, that first bit, is that going to be network is little endian, right? Is it little endian or is it big endian? No. Right, big endian is the downward in networking. Okay, so that's the thing. In networking, it's big endian. So the most significant bit is at the lowest address. Which is fine because Windows is big endian, networking is big endian. The problem is when I'm going to run the server on Linux, Linux is little endian. And so I think for Linux, I'll have to deal with the fact that things are little endian, which will be a problem. It transmits the most significant byte first, right? So in Windows, it's going to read from the lowest address to the highest address. The lowest address has the most significant bit. It's going to read that and send that over the wire first, and that's fine because in the networking, it's assuming that that's the most significant. When it comes to another Windows machine, it's going to read the most significant and put that in the lowest address. But when it comes to Linux, it's going to take that and then it's going to write that with in memory, but in Linux, it's going to take those. Let's say you have a byte. It's going to take that byte, write it into memory, but when Linux looks at memory, you're going to have the most significant bit at the lowest memory address. But in Linux, the lowest memory address is supposed to be the least significant bit. So it's got to be reversed, basically. Okay. So, connected to server. Boom. Okay, so here we go. We're going to want to extract the first bit, which is just bitwise ended with 1. And that gives us the we have a byte and it's all the way at the left. Right, right. It's all the way at the left, so we want to extract the highest value in the byte, which is it's going to be the highest value in that. Right, we're only going to be looking at a 1 byte. So the first, all the way up to the opcode. So the first bit, we want 1, 1, 2, 3, 4, 5, 6, 7. So we want. Yes. Yes, we have 1 byte. So in hex it's 80. Okay, so that's the fin. We're gonna ignore RSV1, RSV2, RSV3. Then let's have the opcode. It's in the first byte as well. And it's the last 4 bits of the... I could do binary, but it's the last 4 bits of... it's the last 4 bits, which is 15, right? Which is F in hex. So we have that, we have the opcode, and then we have mask, which is a char. It's in the second byte, most significant bit. So again, like this. And then we have the payload length, which is 7 bits. So that will fit in a char as well. So payload length. And that's the second byte. It's 7. So it's... Wait, no. 7F. Right. Now, here's the thing. I don't really know what I'm expecting here. So... here we go again. So it's not just that. There's also some kind of weird thing going on where it still thinks it's connected. I think when I drop the connection, yeah, when I drop the connection, it's on an error, but it doesn't get a disconnect message. Is that what it is? I don't get a disconnect message? On air, on open, on message. On close, it should close the socket, right? So... okay, so fin... the opcode is... the mask is... okay, so we know this is wrong. Wait a minute. No. So this isn't a char. This should be an unsigned char. I think it has byte type. Uchar T. Uchar. Where is uchar defined? It's in Windows, so I don't want to use that. It's weird. WCHART is in... WCHART is defined, but then unsigned char. This is why fucking Windows... yeah. My own stuff, I don't have this problem because I have my own header that has all that, but when I'm doing stuff that potentially someone else would use, I can't do that, so... okay. Wait a minute. Wait a minute. Doesn't Windows have uint8? It does. That's what I should use. So, uint8t. Okay. Yes, I know. I know. Oh, I somehow set this to read only. I don't even know how I did that. So it's still all fucked up. So the payload length is 13. What is the payload length actually? The payload length should be, so it's 1, 2, 3, 4. So it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Okay. So the payload length should be 13. And it is 13. So the payload length makes sense. Let's just look at this. Let's look at the buffer's first byte in binary. What does it look like? Right, so the fin is, it's 1, which is the fin, I think. 0, 0, 0. And then I think the last 4 bits are the opcode, right? What? 1, 2, 3, 4. And so the opcode should be 1. And the fin should be 1. But the fin is not 1. And the opcode is 1. The opcode is 1. Fin is not 1. Should be 1. 1, 2, 3, 4, 5, 6, 7. Yeah, that's right. It should grab. Oh. Okay. Okay. Opcode's fine. Fin's wrong because we do this. That grabs that bit. And then we need to bit shift it. So we need to bit shift it to the right by 7 bits, right? 7 bits. Same thing with the mask. The mask has to be bit shifted by 7 bits. And then this guy we can leave because so fin is this is an unsigned int 8. So fin is 1. The opcode is 1. Fin is 1 meaning it's the last message. The opcode is 1 meaning it's text. Right? The mask is 1, which is correct, and we're going to enforce that. And then the payload length is 13, which is correct. So now we're going to enforce that. So I'm just going to check here. If the mask is not equal to 1, then we're going to have a problem, and we're just going to return. What are we going to do on socket message? On socket message, and if there's a problem, I'm just going to close the socket. Yeah, that's all I'm going to do. I'm just going to close the socket. So if the mask is not 1, I'm going to say close socket. The socket. That will close it. Yeah, but then I need to know that I've closed the socket to get out of here. So handshake on socket message. So if on socket message is false, then we break out. Right. On socket message, and if there's a problem, then we break out. On socket handshake. If there's a problem, then we socket as a problem. Yeah, this could be cleaned up a lot. If we get an error there, this is good. It's sad. Otherwise, so here we just say error is true. Error is true, and then here, outside of this, we would just say if error, right? So if an error has occurred, then we're gonna break, and we're gonna close the socket. Okay? So we can get rid of this. Right? Failed, error. If error, close the socket, then break. So here we don't have to do this. Here we can just say error is true. So if this works, handshake is true. If not, then error is true. If we have a handshake, then we say on socket message, and we can just say error. On socket message, and if it returns true, then there's an error. Wait, I'd rather say return true when something goes wrong. When you look at code, you assume that it's returning false if there's a problem. So on socket message, and if I return on socket message, if it returns true, then it went well. If it says false, then something went wrong. I don't have to do this, but I will printf a message. Client message mask bit set to 0. So if the mask is not 0, there's a problem. I'm gonna go here and yeah. So now what do we do? So get all this stuff. If the mask bit is not 1, there's a problem. I'm expecting there to be masking. That's all we do with the mask. Not sure if we're actually going to use the fin. Opcode is text, so I'm only going to allow a certain type of text, I think. It's just going to be, yeah, I'm still not sure what I'm going to do. I might have binary, I might have text. We'll see. And then we have the payload length. Yeah, what I'm gonna do instead is just move this down here. So the fin, the opcode, and then the payload length. We'll move that down. So we get the masking. If it's not 1, message mask bit message mask bit must be 1. Message mask bit must be 1. Message mask bit is 0. Must must be 1. Return false. Otherwise, we get this stuff. We get our fin. Not sure if we'll use it. We'll get the opcode. We'll get the payload length. Extended payload length. Not sure if I need that. The masking key is... So we're going to have the masking key. So what do we do once we do all this stuff? If masking is used... If masking is used, why does it show extended payload length optional? That's if you have extensions, I guess. So payload length. Then, so there's 4 bytes of nothing. And then the masking key. This field is absent. This field is absent if the mask bit is set to 0. So is the extended payload length also absent? If masking is used, the next 4 bytes contains the masking key. So I guess it's not. I guess we're just going to have the masking key. So the next 4 bytes are the masking key. All subsequent bytes are the payload. So now we get 4 bytes, which is a 32-bit integer. Masking key. So masking key is the next 4 bytes. So we read the payload length. So this is the first byte, the second byte. Then we're going to read 4 bytes, and that's our masking key. I wish I could just do this by just casting it to a pointer, but it doesn't seem to work. So buffer, we have the first byte, the second byte. It's going to be the third byte. That one, and then another byte, and then another byte, and then another byte to make it up. So it's going to be this guy. Bit shifted to the left by 24 bits. Board with this guy, bit shifted to the left by 16 bits. Board with buffer 4, bit shifted to the left by 8 bits. Board with buffer 5. That's the masking key. That's the thing, I've got no way to confirm that this masking key is actually correct or not. Two, three, four, 5. Okay, so next 4 bytes is the masking key. All subsequent bytes are payload. Okay. The opcode field defines how to interpret the payload. If it's 0 for continuation, 1 for text, 2 for binary, and other so-called control codes that will be discussed later. So I'm either going to be doing text or that. The fin bit tells whether this is the last message in a series. If it's 0, then the server keeps listening for more parts of the message. What does that mean? Otherwise, the server should consider the message delivered. More on this later. So I'm going to receive like a portion of a message. Like, yeah. So decoding payload length. So to read the payload data, you must know when to stop reading. That's why the payload length is important to know. Unfortunately, this is somewhat complicated. To read it, follow these steps. That's just the payload length, and then with that. So read bits 9 to 15 inclusive. and interpret that as an unsigned integer. Um, hmm. 9 to 15, which is the payload length, right? Read bits 9 to 15. I already know it. It's 13. That looks right. Decoding the payload length. Read bits 9 to 15 inclusive and interpret that as an unsigned integer. Right, which is what we're doing here. No. One, two, three, four, five, six, 7. Right, 7 bits. Right, okay. So read bits 9 to 15 inclusive. Interpret that as an unsigned integer. If it's 125 or less, then that's the length. You're done. Right. If it's 126, I guess if the payload is too long. If it's 126, go to step 2. If it's 127, go to step 3. Okay, so step 2 is read the next 16 bits. Oh, I see. So you could have extended payload length. Ah, and so you can't just read the masking key and stuff like that. You have to know where in the buffer you're at. So you read the mask, you read the fin, the opcode, you read the payload length, and then you check this. So if payload length is less than 125, else if the payload length is 126, else because what if it's something other than that? If it's 127, go to step 3, and if it's not, then we don't know what's going on. So I'm just going to assume it's 127. If the payload length is less than 125, then that's the payload length. We're good. So what do we do? In this case, the buffer index, so where do we start reading, is 2. That's the next place to start reading with the masking key, right? If it's 126, then if it's 125 or less, 125 or less, so if it's 126, it's the payload length, because it's only 7 bits, right? Read the next. What's the max you can have? 127 is the max. Okay. Read the next 16 bits and interpret those as an unsigned integer. You're done. So that's the length. You're done. If it's 126, go to step 2. Step 2 is read the next 16 bits and interpret those as an unsigned integer. If it's not, read the next 64 bits and interpret those as an unsigned integer. The most significant bit must be 0. And then you're done. Read the next 16 bits. So what I'm going to do actually is I'm going to say this is a 30, or we'll say this is a 64-bit integer because it's saying 64 bits, but the last bit is 0. So we're going to say this is a 64-bit integer. If it's less than or equal to 25, then the buffer index is 2. Nothing else to be done. If the length is 126, then we need to read the next 16 bits, which is 2 bytes, right? So the payload length is going to be the next 2 buffers, right? Which is 2. Bit shifted to the left by 24. Or that with buffer 3. And then your buffer index now is going to be 4. Right? Is that right? We did buffer 0, buffer 1. Now it's buffer 2, so those 16 bits, right? And that's your payload length. Whoa, 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 it's not 24. It's just 8. 16 bits. It's actually going to be this. This will be 64 bits. Wait a minute. Bits or bytes? 16 bits, which is 2 bytes. Right? 64 bits. Right, 64 bits, which is so 4 bytes is which is an 8-byte. There must be an easier way to cast this to a 64-bit number. How did I do it? How did I do it further up there? No, 64 T. Oh, I extracted it from there. But I can't just say, well, we know what the buffer index is going to be, right? The buffer index, the next buffer index is going to be, you're going to be at, it's 64 bits, which is 8 bytes. And so we were at, so we read 2 more bytes. So 1 plus 2 is 3, plus 1 is 4. So 1 plus 8 is 9, plus 1 is 10. So the index is 10. So now when we get to the masking key, this is the buffer index. This is going to be the buffer index plus 1. There's got to be a better way to do this in there's got to be a better way to do this. I'm sure there is. Can't you just say payload length is equal to reinterpret? Is that what I have to do? Reinterpret cast to a U int 64. So you just say buffer at index 2. So pointer to buffer at index 2. Reinterpret cast it to a pointer to an unsigned 64-bit integer. And then you just say it's equal to that. Okay. That should work, right? I think that will work, but I'm not sure. Well, we could try that with the masking key. So yes. So the payload length is 13. So we just go from there. What's our masking key? Our masking key. Oh, this is the number. It's a 32-bit integer, 4 bytes. Let's copy that value. And then let's change this. So let's it's reinterpret cast to uint 32t pointer. So you say the buffer at whatever the buffer index is that we're at. Cast that to, we're pointing, it's not a pointer to a char, pointer to a uint32. Then the masking key is different. Yeah, because it's not. So we said buffer index is 2, right? So you then read it from buffer index 2. So buffer at index 2, a pointer to this char. Cast that as a pointer to a 30-bit integer. Yeah, this never works. I don't know why. That's a dumb way to do it. That's a dumb way to do it. Okay, but it's not a char, it's actually like bytes. I don't understand why it doesn't work, because no one's doing interpret casts, so but shouldn't that work? I thought I used to do that all the time, just casting it. Yeah, so you say bytes, cast it to a pointer to an int. And then there you go. Wait a minute. Do this one, then you do 8, 16, yeah, then 24, right? Buffer index is 2, buffer index is 4, buffer index is 10. Okay, what if we just say forget about the C++ bullshit here and we just cast it like that. Yeah, how come it gives a different value? That's weird. So, okay. Like, you cast it to a pointer, then you dereference it. You're basically tricking it into thinking it's an UN32. Oh, I was expecting the masking key to be the same between sessions. That's not the case. So the masking key, it shouldn't change. Okay. All right, fuck it then. That's, man, you can't do that. That's what? I don't think you have to convert to cast to inside chart. It's just taking the bits and shifting them. It's not interpreting them at all. And ORing that all, and then you get this thing that then, yeah. The value 24 is an int, so will also be converted to an int before the shift to perform. Right. On your system, a char is apparently signed. Char is always signed. What are you talking about? And will then be sign extended when converted to int. Is that why it's happening? There's some kind of weird thing with but the bits are the same. When you bit shift it, so we're converting a char to an int. There's an implicit promotion to a signed int in your shifts. That's because char is apparently signed on your platform. Why do they keep saying that? You have char and you have unsigned char. I've never heard of char being unsigned. If char was unsigned by default, why would you have unsigned? And why would you make it sign or bad? The common thing to enter implicitly. In fact, none of this would work otherwise because okay, I bet if I change this, it's not going to make it any difference. So if I say unsigned char, or better yet, I could just say uint8t. I don't think that's going to change anything. And that hasn't been a problem so far. Oh, it does. It takes a char pointer. Okay. So I can't do that. Yeah, I can't do that. Okay, let's do a little experiment then. If yeah. Let's forget about this for now. I'm assuming this is gonna work because I've been doing this so far without issue. So this is gonna, I'm gonna have to come back to this to cast it to an unsigned N64. Like this will actually be buffer 2 bit shifted to the left, so it's gonna be 8, 16, 24. I don't want to write this huge thing out if I don't have to. I really want to just cast it. Is it because I'm doing some kind of thing with the sign? So This is a signed char. It's gonna get cast to an int. Is that what the problem is? What was the... Fuck. My SHA and yeah, that might be a problem. The bytes could be in little endian order, and the integer in big endian order. I don't understand what that means. If it's... Yeah, so this is exactly what I'm doing. Oh, because you may have alignment and stuff. Okay, so we can't do this. We can't do this. Fuck. So, okay. So it's gonna be 8, 16, 24, and 32, and then 40. 48, right, 8, and then 56, so 56, so this might actually not work. My SHA and my base 64 might be fucked if it runs on a little endian system. That's not good. It's fucking big endian, little endian, man. The internet uses big endian, Windows uses big endian, and then Linux goes off and does fucking little endian. Like, of course, we have to make things more complicated than they need to be. Everyone could have just chosen to use the same one, but of course that didn't happen. Of course that didn't happen. So now we were at 48, right? Yeah, 48. I don't want Vim to wrap like that. I need to turn that off. 10 would be the next one. So you do 8, 16, 24, 32, 40, 48, 56. Let's assume that this masking key is correct because I think it is. How do I do this in Vim actually? Set no wrap. I'll have to put that in my Vim RC, but let's just say set no wrap. Boom. That's what I want. That's what I want. If I say edit, I got Vim. Yes, okay. Set no wrap. Oh shit, I closed the whole thing. The whole thing. Yeah, I closed the whole thing. Okay. Let's go back to Fenrir. Yeah. And then I'm gonna open our yes, I'm gonna open index.html. And now I don't have wrapping. So let's assume that the masking is correct and I have the masking. Now what am I doing? So we have the payload length. We have the actual payload length now as a 64-bit integer. Oh, but it also said the most significant bit must be 0. So you actually don't take, or yeah, you do all of this and the most significant bit must be 0. So once we have this payload length, if payload length or if payload length end with, so what is the most significant bit? It's gonna be 1, 2, 3, 4, 5, 6, 7, 8. Right? It's 64. That's the max, right? And then if you set this to just 7 and Fs. $16 digits, so 15 Fs. Payload length, extended payload length, bit, extended payload length, most significant bit must be 0. So what you do is you end it with that one. Wait, no, it's not that. that right? Yeah, end it with that 1-bit set. Well, how many characters? 2 characters is 1 byte, and it's 8 bytes. Right. So it's a 6. You get 16 characters. Right. Yeah. 15. Yeah. So if that bit is 1, then when you say if, it's going to be non-zero. So if it's true, you're good. Or no, if it has to be 0. So if it's true, then there's a problem. Return false. Okay, so this may not be exact, but it's something. So we have the payload length now. We have the payload length as a 64-bit integer. You're done. Now, reading and unmasking the data. How do we do that? So, if the mask bit was set, and it should be for client-to-server messages, read the next 4 octets. 32 bits. This is the masking key, which we're doing. It's a 32-bit masking key. Once the payload length and masking key is decoded, you can read that number of bytes from the socket. Let's call the data encoded and the key mask. So you have mask, which is 4 bytes, 4-byte mask, and then you have encoded. Let's say they have the string hello. Okay. To get decoded loop through the octets, bytes, aka characters of text data, so through the bytes of encoded, with each byte of encoded, and exclusive OR the octet with the I modulo 4th octet of mask. So you do I modulo 4, the index I modulo 4, that gives you the index into the mask. In pseudocode, what that happens to be valid JavaScript. In pseudocode, that happens to be now you can figure out what decoding means depending on your application. Okay. So, okay. Now let's look at the first character and see. So the first character, the first character is going to be buffer. After we do this, what we should do is we should say buffer index is incremented by, well, we looked at 1, 2, 3, 4, so incremented by 4, right? It's 3, so plus 4 is the next buffer index, right? Okay. I'm gonna take a break. 1 second. Okay. So we say buffer at the next available buffer index. That's going to give us our next byte. If I take this and then I exclusive OR that byte with so you say masking key. Oh, so the masking key could just be an array then of, doesn't have to be in a 32-bit integer, but okay, so masking key, or it with the masking key at what index? It would be 0. This would be 0 modulo 4. And let's just see t value. Or let's just say that's a char, and let's see what happens here. I called it playload, not payload. Okay. Oh, but you can't, yeah. It's easier if we do it that way, but we can't do it that way. Should I just have it separated? Knowing that this is how it's going to be, yeah, I think it should be separated. Then we actually don't have to do all this stuff. So we can just say u int 8t masking key, and it's an array. Masking key is buffer at buffer index, right? So we have an array, masking key, extract that, and then now we can actually say it this way. Makes it easier to read that. So what's our value? Our value is H. So, okay. The only thing I'm worried about is that this is not going to work with Linux. I'm still really worried about endianness. That's a fear I always have now. So, okay. How do we do this properly then? We're going to iterate over the rest of the buffer and write that to a string. Because I'm assuming the message is a string right now. So so on socket message, and then yeah, what we'll do, I guess, is we'll have a string, which is the message, and then what we would do is we'd call, like, we'd say like on message and pass in the message or something like that, right? I think this should actually be a it should maybe be a 64-bit because the length could be a 64-bit number, right? So the number of bytes can be a 64-bit number. So again, long payloads and stuff, we'll have to deal with that later, but for now, this is good enough. So we can just say the message is plus we're going to take this exclusive OR with that. It's going to give us an integer. And then what happens if we try to do this? It'll probably work, but yeah, that still does work. Okay, I don't have to say like static fast char. I'll just do that just to be, I don't know, just to say. So what you do is you iterate over that, and then it's the buffer index, which was that, the available buffer index, plus I. So that's the byte that we're at, and then this is just I modulus 4. Look at that. So it sends us a message. We receive the message. So the client connects. We establish the connection. The client then sends us data. What's the problem with this here? What's it complaining about? Arithmetic overflow. Right, because you have this and you're left shifted by 56 bits. So you'd have to then static cast this buffer. He might be right about the mem copy. Man, this fucking endianness stuff pisses me off. It's a worry I have, and I'm testing everything on Windows, but it's gonna have to run on Linux. So eventually, so on socket message. Yeah, this. I'll worry about this later with the message because we don't have long messages right now anyway. But worry about that later. So basically, if my message length is 126, then we do this, and if it's 127, then we do this. That would be a long message because that would have to be beyond this, and this is 16 bits, right? And 16 bits, what's the max value of 16 bits? It's like 16,000 something. I'm not gonna have messages that are that long anyway, so this probably isn't gonna be something I need to worry about. But yeah. So on socket message, we're doing the handshake. We're now receiving socket data. That's working. What's left is to be able to send data back to the client, and then being able to send data back to the client. For now, I'm just gonna let's just do this. Message. Oh, and then let's do that. So let's just do this for now, so I can see what the message is that comes in. Right. So connection established. We receive 478 bytes. We send 129 bytes. Then we receive 19 bytes, and it's hello there. Okay, the next thing we have to send data back to the client, and then I guess that's it. We don't have to do anything with closing, like with sending a close message or anything. I guess that's it. It's just the handshake and then messages. I don't know if there's anything else. Okay, then there's this fin thing. Okay, there's some other stuff going on here. So what else do they have to say? So I'm done with this. On message, on error, on open, on close. Let me go back to here. Socket closed. Message received. Connected to server. And then whatever the error is. So large bits of data is a thing we still have to worry about. So connected to server, and then we get this. Okay, now if I close the connection, socket closed. Okay. I'm gonna have to, so the rest of the work will continue in the next video, but let's just wrap this up by reading this here. So the fin and opcode fields work together to send a message split up into separate frames. This is called message fragmentation. Fragmentation is only available on opcode 0 to 2, so binary and text. Recall that the opcode tells what a frame is meant to do. If it's 1, the payload is text. If it's 2, the payload is binary. What's 0? If it's 0, the frame is continuation frame. This means the server should concatenate the frame's payload to the last frame received. Okay, so it receives the next frame. You just take the payloads. Okay, so you can have a payload broken up across multiple frames. Okay, so if it's 1, it's text. If it's 2, it's binary. If it's 0, it's a continuation. So, but then what's the point of having the... Right, so you get 0, it's a continuation of the last one. You get a continuation of the last one. Then once you see a fin of 1, then that means it's the last frame. Is that right? If fin is 1. Yeah, if it's a 1, it's the last frame. So if it's a 0, there's more frames. So we just keep the message and then we wait to get more data. And then if it's a 1, we know it's the end. Okay. Should concatenate the frames below that. Here's a rough sketch in which the server reacts. So client, so fin 1, opcode is 1, and it's text. So it's hello. So it's text. The server complete process complete message immediately. So it's just hi. Client as 0, meaning it's not the last one. It's text and new message contains start, and then 0, 0. It's a continuation. But if it's fin 0, doesn't that imply that it's a continuation? Happy New. And then fin 1 year and Happy New Year to you. This is a mistake. It's not hi, it should be hello, right? They're saying what they received. Oh no, that's the response. Okay. It's kind of weird to say it that way, but okay. Notice that the first screen. Okay, so I understand this, so I can implement this. That's not too bad. Basically, Message broken up across multiple frames. I'm not sure why it would do that, but I guess it's possible that that happens. Pings and pongs, the heartbeat of WebSockets. At any point after the handshake, either the client or the server can choose to send a ping to the other party. When the ping is received, the recipient must send back a pong. So we have to handle that. You can use this to make sure that the client is still connected. For example, a ping or pong is just a regular frame, but it's a control frame. Pings have an opcode of 9, and pongs have an opcode of A. When you get a ping, send back a pong with the exact same payload data as the ping. For pings and pong, the max payload length is 125. Okay, you might also get a pong without ever sending a ping. Ignore this if it happens. So we need to handle sending data back to the client. We need to handle replying to a ping. I don't think the server is ever going to send a ping. I'm just going to have it reply to pongs. If you've gotten more than one ping before you get a chance to send a pong, you only send one pong. But then I'll get a ping, I'll send a pong, and I'm gonna, okay. So I need to be able to handle a ping, I need to be able to respond with a pong. I don't think I'm gonna send out pings. And yeah, so we do the send data back, handle, respond with a pong. To close a connection, either the client or server can send a control frame with data containing a specified control sequence to begin closing the handshake. So there is a procedure. Upon receiving such a frame, the other peer sends a close frame in response. The first peer then closes the connection. Any further data received after closing of connection is then discarded. So we still have quite a bit more. We've got the handshake. The client can send data. We receive the data. That's great. But we still need to handle long messages. We need to be able to send data back to the client, and we need to be able to respond with a pong when they ping us. I don't think we would ever ping them. No, I don't think we would ever ping them. I could do, like, after a certain amount of time, if we haven't received a message from that client, send a ping, and if you don't get a response after a certain amount of time, just close the connection and say that the guy disconnected. So sending data back, closing the connection, and then responding to pong. So we have 3 more things to do. I mean, I'm happy that we've at least got this working. Okay, so that'll be next time. 3 things left to do, basically, to get the basics of Fenrir up and running as a WebSocket C++ library. That will be next time. Yes.